Okay, this is the Unit 5 MCQ test corrections. Okay, this first question here we have the disk is at rest and the four forces with the same magnitude are briefly exerted on the disk. There's negligible friction. Which of the following describes the motion of the disk after the forces are exerted? So we see that the forces will make this disk move in a clockwise direction. And then since we know that there's no more, like the forces are stop. Like we know that there's no net force after the forces have already exerted, so that means the velocity should stay constant. So that's why we have this one as our answer. And I got this one wrong because I don't know. I think maybe I just wasn't thinking or I was being rushed or something. But yeah. Okay, next we have this question. This graph shows angular velocity as a function of time. For a point on a rotating disk, the magnitude of the angular acceleration of the disk at t equals 2 is most nearly, and since they give us angular acceleration or angular velocity here and t here, we can just find the slope at 2 by doing y2 minus y1 over x2 minus x1. So we can just do 3 minus 1, and then here we can do like 7, or actually this is 7, this is 6.5, and this is 3, it's like 3.5. So we have 3 over 2 is equal to 1.5, so that's how we get this one. And I got this one wrong. I got this answer because I didn't realize that this was in 2s. I thought this was 1, 2, 3, 4, 5. So that's one of my answer, which is half of what the actual answer should be. Okay, now this question. The figure above shows a uniform meter stick that is set on a fulcrum at its center. The force of magnitude F toward the bottom of the page is exerted on the meter stick at the position shown. Which of the following positions must an upward force of magnitude 2F be exerted on the meter stick to keep the meter stick in equilibrium? So we know that if it's just this force, it would go down this way. It would rotate this way. So we would need a force right here because we see we have double the force, and so we need half the length in order to get the same torque. So it should be here at C. And wait, upward force. Oh my God. Sorry, not at C. It actually should be here at B, because so it counteracts it. Because if it was at C, it would actually keep it rotating. But it should be here at B to prevent it from moving. And that's basically how I got the question wrong, because I didn't realize that. And I also thought it was a downward force, so I thought it should be at C, but it should be at B, right here, because it's double the force, so you need half the length in order to generate the same torque. Okay, the last question I got wrong was, a person diving into a pool is initially rotating in a position with her legs pulled inward as shown above. The person then stretches out her legs as shown in the figure 2. Which of the following quickly describes the rotational inertia and angular momentum? So we know that when she has her legs pulled out, her rotational inertia increases because her mass is more spread out. But then there's no mention of a net force or a net torque acting on the system, so we know that angular momentum has to be conserved. So that's why it should be this one. And even though her rotational inertia increases, her velocity will decrease in order to keep the same angular momentum. And thank you.